I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students. Pray you just help us to understand a little bit more about Lie groups and the algebras, just to give us insight in the time we have today, Lord. In your name I pray. Amen. Okay, as I was mentioning to you guys, I think I'm going to, at least for the moment, skip past Theorem 2.21. Theorem 2.21 gave us, well, I would say it gave us like a non-standard notation theorem for various, we will say, properties of the, what we'll soon call big adjoint and little adjoint. So let's try to, I think this will be more memorable and serve a larger purpose if we try to talk more. So I'm going to try to talk today at least a little bit more about just like formally what a Lie algebra is. That stuff, even when I'm sleepy, I can talk about. So, but this we can talk about too, the adjoint mapping. So this is the big adjoint. And it works like this. If we have G a matrix Lie group with Lie algebra frac G, alright, then for each A in the group, capital A in the Lie group, we define adjoint sub A, which is going to be a mapping from frac G to frac G. In other words, what we're going to soon understand, it's in fact a linear transformation on the Lie algebra. All right, I believe. Let's see here. Yeah, linear map. And the formula that it's defined by is basically conjugation by A. So add A of x is equal to A inverse XA, right, for each x in frac G. All right. Now, so what's the first thing he tells us? I mean, what is this? So this probably is only something that we can do in matrix. Like this exact formula probably is only going to make sense in the context of like matrix Lie groups. If you think about the more abstract concept of a group, all right, the algebra and the group are different objects. Like perhaps the algebra is a set of differential operators, whereas the Lie group is a point set, you know. And you couldn't just multiply before and after an operator by, you know, something in the point set. It wouldn't make sense. But there's a generalization of this which makes sense in like the more abstract Lie groups. But here it's matrix Lie groups, which is a nice starting point, right? The fact that that's linear, I think, is immediate from the formula, right? What else can we say about it? Well, proposition, change colors here. Proposition that follows tells us a little bit about it. Let's see what it says. So the proposition 2.23, we have G a matrix Lie group with Lie algebra frac G. Let GL frac G. Before I tell you what this is, what should this be, guys?
General linear group of
the invertible matrices among the Lie algebra.
Essentially, but I think it's actually the invertible transformations, but
right.
I mean, potato, I guess, but yeah, transformations. Then, okay, so the adjoint of A is an element of GLG. In other words, it's an invertible linear transformation, in fact. All right. I'm assuming what? I should say really this before. A is where? Where is A from? A is in G. All right. What is the inverse?
It's going to be add the A inverse.
Yeah, add of A inverse is equal to what?
Add of A inverse.
Okay, yeah. Something gets lost in the English of it. Add of A inverse is add of A inverse. Well, yes. That seems rather tautological, except it's not. All right. And more than that, the map A maps to add A is in fact a group homomorphism of G into GLG. So that's, I mean, I guess you got to strip off, strip off the A. Rather, we should think about A maps to add A is this assignment, if you call it, say, I need some other letter, I don't know, eta. Then eta is a homomorphism from G to GL frac G. This is a homomorphism. Eta is a homomorphism of groups. Furthermore, for each A in the group, the adjoint of A satisfies the adjoint of the commutator is the commutator of the adjoints. Also, the adjoint sub A of xy is equal to the commutator, I should say the Lie bracket, of the adjoint of A of x, adjoint of A of y, for all x and y in frac G, and A, of course, and A and G. I mean, it's true for HJ. I should say for each A and G, this identity is true, of course, is what I mean, but so he says, proof, easy. Proposition 2.17 guarantees that add A of x is actually in G for all x and G. In other words, that's what's proved in what I just skipped over. Well, no, that's not even it. It's proved 2.17. We might have. I don't. Did we do this one?
I feel like we might have.
G, a matrix Lie group with Lie algebra G. Let x be an element of G.
Yeah, we did that.
And then it's closed under. Yeah, we did do that.
Mm-hmm.
Yeah. So that was 2.17. We actually proved that we proved that conjugation by the group keeps you in the algebra.
Mm-hmm.
So we've shown that.
First.
We've shown that if this is in the Lie algebra, then this altogether is in the Lie algebra.
Yeah.
We would prove that another day.
Yeah, we did that.
So that shows that this mapping, the adjoint of A, is at least into, right? Linearity is clear from the formula. Invertibility, well, that's a claim. Can you? I mean, I guess it's fairly obvious that. I mean, I don't really. Let me just check the invertibility right quick because I am very gullible today. Let's see here. So Daniel believes. I want to believe. Let's see here. Add A inverse of add A of x, right? I'll just check one. I'm willing. If it works for this, I'm willing to accept my fate. The adjoint A of inverse. We'll use your formula in a second here. Then this is A inverse XA. Oh, it's obvious. I mean, it's just.
Yeah.
I'm sorry. I'm just. As I write it, I'm just like, oh well, duh. A inverse inverse. A inverse XA. And then
A inverse.
A inverse because this allegedly is, add of A inverse, so you conjugate by the A inverse, which is to say A inverse inverse, multiply by inverse on the other side. This is A. They give you back X again. So in other words, the composition of add A inverse with add A is the identity on G. And the opposite order is the same stupid thing. So really, that's it. Okay, so what else do we need to prove? I think that was the easy part.
Yeah.
Well, that's part of it.
That data is a group homomorphism.
Oh, I think when he says proof easy, he just means work it out yourself. I don't think he's actually saying it's a corollary, something he's done before. I think he's just saying, we can work it out.
Right.
By the way, it should not be, no one who happens to be watching these or following along should in any way view what we're doing here as some sort of fair reflection of Brian Hall's book. We are bouncing around, looking at little pieces. There's all kinds of grandiose motivation in this book that I have not said anything about. I mean, he has a big picture of what he's trying to do in terms of taking a homomorphism from one place to another and building it and looking for that, and that's what's motivating. I mean, there's all kinds of motivation. There's motivation out at the wazoo, whatever that is, for all this stuff. Okay, so let's see here. At least we can... the group homomorphism, let's see if we can't prove that. Well, if I have AB, right? Well, that will move, that will map under eta to the adjoint of AB, right? But if you look at the adjoint of AB, acting on X, of course, that's AB inverse XAB, right? Which is sock shoes, B inverse A inverse X AB, which is, looks like to me, the adjoint of B of the adjoint of A acting on X. Huh. That doesn't look like a homomorphism to me.
I mean, with composition. Well, oh yeah.
Looks to me like AB maps to, add B composed with add A. I think this is an anti-homomorphism. Yeah. I mean, that's what I find. An anti-homomorphism is one that reverses the product.
Reverses.
Like, a homomorphism from a group to another group would be the product is preserved. So here I have matrix multiplication goes to composition of, adjoints, but in the opposite order. In other words, I have eta of AB is equal to eta B times eta of A, where this is composition. Huh.
I think, wait, hold on a second.
I mean, that's okay. It's not the end of the world. I mean, it's...
Yeah, I've had this problem before.
Oh, it works if you do, if you make the add A original function AX A inverse, which is what I think they had in the book.
Oh, yeah?
Yeah, I think it's the other way around, AX A inverse.
Ooh.
And I just did it, and it does preserve the product.
The map, A maps to add A is a group homomorphism. Where did you see that?
In the definition.
Well, the definition of the add A should be the other way around.
Oh!
Oh.
Oh, man! Don't let me do that!
Sorry.
Oh, no! Oh, goodness gracious. I'm glad we said that now. If I got much further down the rabbit hole... Jeez. Oh, goodness. That's awful.
I mean, your first one works the other way anyway. I did it the other way.
Here, we'll fix this like this.
Yeah. Yeah, the first one was the same, but the second one works this way.
Wait, the inverse is perfect.
Yeah. There we go.
It's 4:00 p.m.
Shut up.
Where's the military time?
It's messing with my clocks. I'm gonna lock my door now that you get microwave service is over. Messing with my clock. People messing with my clock. I'm gonna fight back here, please. I'm gonna hire somebody to hide under my desk and just wait for them. Come in your microwave and attack them.
Is that paywall? $15 an hour.
Theater. I'll hire somebody at the theater arts person who wants to get in the really interested in character work or something, you know. Somebody devoted to their craft who'll spend the time. Show that they're serious artists. What's that? Nice. What?
Business dress.
That's too rapid to be walking.
I guess yeah. Hammer. I don't know.
Hammer?
The student union is almost here.
I don't know. Okay, I'm sorry. I'm getting distracted here. Okay, so now, fine. Now that we've finally actually working with the adjoint,
Two people walking.
all right, that is definitely a hammer. Is that physics lab? I'm sorry. I'm getting distracted. All right, so this is the homomorphism. What else do we need to prove? This relation here.
It's not too hard.
Not too hard. Let's see here.
So we got
So we do what? We do A, X, Y, A inverse. If I was smarter, I would start with the other side.
what do the brackets mean again?
Commutator. So these are, we're in a matrix Lie algebra, so that's actually the commutator. It's X, Y, minus YX. Is this a university? I sometimes wonder. Let's see here. A, X. And if you use your imagination, you can see an A inverse. A, Y, A inverse minus A, Y, A inverse A, X, A inverse. You notice I inserted these, who says you can't have something for nothing? This and this I created from the thin air, yeah. And so now what we're looking at is this minus that, right? And that is exactly the commutator of AX A inverse, AY A inverse. See, this would actually be a friendly linear homework.
Mm-hmm.
Maybe I'll ask this one, if I can remember. So here we have add A of X, add A of Y. All right. What is that saying? By the way, I guess we're also thinking of this as a matrix, aren't we? Is that right? Because I guess you either look at these as, these are, let's see, that goes from where to where, that's,
I think that's from G to G.
oh, that's in the
Or
Lie algebra.
G,
Yeah, that is in the Lie algebra about being silly. So that is what we're taking the we have what that says is that the bracket in the Lie algebra, right, maps to the. I mean, what is that saying? It's let me write it kind of more symbolically. We have like psi of the commutator of x and y, right, is equal to the commutator of psi of x and psi of y. So I think that's to say that psi is a what it's a Lie algebra homomorphism, I believe.
Okay.
So in fact, the adjoint of A is in fact a Lie algebra automorphism of the Lie algebra itself. It's a, well, I don't know if auto is warranted yet. I'm not. Is it? I don't know about. I'm not sure about the. I'm not sure about if it's a bijection. I can think about that more, but at the moment, but if I forget, I'm rusty on these things. But certainly, it's a homomorphism of the Lie algebra to itself. I suspect it's an automorphism, meaning it's actually a. Well, I shouldn't say that. I don't know. Conjugation's complicated. What does it do? Who knows? There's got to be some kinds of Lie groups or some kinds of Lie algebras for which it's an automorphism, probably, and some that aren't. Automorphism meaning that it's a Lie algebra isomorphism. A Lie algebra isomorphism is an isomorphism in the sense of linear algebra that also has a preservation of brackets. So automorphism in the linear algebra is an isomorphism from the vector space back to itself again. It's an invertible endomorphism. All these morphisms, so many morphisms.
What's the point?
I mean, I think it is an isomorphism. We found the inverse, right?
But we didn't find the. We found the inverse. Yeah. I'm trying to decide if it's the right mapping we found the inverse of. I mean, there's a couple different
Seems
things.
like a different mapping.
There's this eta map, right?
Right, but that's not.
But that's not the one we're talking about.
Yeah, we found the inverse of the adjoint.
Right, we found the inverse of the adjoint A, which is actually the one that's. I mean, in my notation, psi is at A, right? So yeah. Okay. So, unless you've swindled me into something, but there's no multi-level marketing involved, it's probably okay. That's right, I went there. Sorry. So what that would mean is that the adjoint at A gives us an isomorphism from the Lie algebra back to itself again.
Okay.
Now, by the way, something like this is an example of a group representation. What is a representation? Getting ahead a little bit to chapter 4. Just sowing some of the seeds of the basic ideas here. A representation is a homomorphism from a group into a set of linear transformations. So like invertible linear transformations, of course, if it's a homomorphism, it's got to go into invertible things if the group goes to a group, right? So this actually gives us a representation of the Lie group on the Lie algebra. Okay, and that's the adjoint representation, I believe. There's a few different adjoints floating about, though, so let me not. I'm sure at some point somebody with more authority will come through and say, no, you cannot call all of these things the adjoint. You need to give them separate names and stop confusing the students. Such a kind-hearted person, as far as I know, has not said with authority these things yet, so in the meantime we will continue our tradition of confusing you guys. And me too. Alright, so, where was I? Alright, so there's that. It actually was easy. That was, for once it said easy, and it was actually easy. Feel better about my day. He says, since the Lie algebra is a real vector space with some dimension k, GLG is essentially the same as GLKR. So he's like, this is basically isomorphic to GL K by K matrices over R. In other words, this is like K by K invertible real matrices, right? You can use those to represent, it gives you a matrix version. Okay, I mean, it's kind of stupid. We started with a matrix Lie group, and I'm saying you get a matrix version of the group. This is more exciting when your group is not a matrix group, right? But anyway, there it is. And so thus we will regard, fighting for that word today, GLG as a matrix Lie group. It's easy to show that adjoint is continuous, and so is a Lie group homomorphism. So the adjoint without the A. This eta is continuous. All right. I believe that. The formula for eta is in terms of multiplication by matrices. It's made of continuous stuff, so it's continuous. I mean, it's got a there's a formula. Okay. Not a rigorous argument. Yeah, it's right here. This one. Oh. Yeah. I mean, this one rather. Right. So the way A appears there relative to itself and relative to X, everything going on there is a continuous product of matrices. It's inversion of a matrix, but that's, again, a rational function of the components of the matrix, which is itself a continuous operation, provided the inverse exists. But the inverse exists as part of the assumption that the Lie group is a subset of the set of linear invertible matrices. So we're good to go. There's an associated real linear map. X goes to add little add X from the Lie algebra of G to the Lie algebra of GLG. All right, now we're playing with fire. So he's like, so there's a little add X. What's he say that one goes from?
Frac G to, well,
Yeah, from the Lie algebra, yeah, from frac G to
GL frac G.
yeah, like little GL of frac G, let's say. I would assume that, oh, well. Oh, I'm sorry, and I haven't said this right. Little add, let's say, all right. Little add is the mapping X maps to that. This is the little add I was warning you about. What's the relation between the little add and the big add?
capitalization.
Capitalization is not the right answer, but it's funny. Don't make me laugh. You don't understand. When I laugh, I cough. When I cough, we all suffer. Come on.
Something like the push forward like we saw last week.
Right. I think what you're really looking at is the derivative of the big adjoint. So in my current notation, I had eta, right, going from big G to GL. So I think in my current notation, basically, add is essentially the derivative of the eta map. It's the push forward of it. It maps from the tangent space of.
So is it little add goes from X to add of X, and then add X goes from frac G to no.
It maps little x to out of x.
So then what's the frac G and they're elements
That's
of.
the sets, yeah.
Yeah, let's see here. So this would be like the differential at the identity, I think. Would be add. To be more pedantic, di eta of x should be equal to add x, if I'm thinking correctly here. That would make sense because this, G basically, the tangent space of the identity of G is understood to be the Lie algebra of G, so that has like x as an element of it. And then you push forward that over to the tangent space in the range, the image of the identity, which would be, this would be an element, essentially, of the tangent space at the identity of GL frac G, which, by the way, is
GL.
little GL of frac G. It's the Lie algebra. That going back to the discussion we had about the relation between like invertible matrices versus the tangent space of all invertible matrices just being arbitrary matrices.
Oh yeah.
I mean, okay. And then, but he says something more interesting. And this ties back in with the stuff at the start of the chapter, which I have not done justice in communicating yet. He says there's a connection between the little ad and the big ad, and his connection is this. So he says the connection is e to the adjoint of x is equal to the big adjoint of what? E to the x. All right, so
Right, that's like what we saw last Monday.
yeah, so I mean, it's the difference between how he's selling the Lie algebra versus how I'm trying to sell the Lie algebra in terms of being the tangent space of the identity versus being this implicit thing wrapped up in the process of exponentiation, which is, I mean, I think his book proves that that's a more efficient way of thinking at this level, but to me it's kind of more divorced from geometry. I'm not happy about it. Does this make sense? I mean, so we're exponentiating this operator, and what's this?
The bigger operator of the exponent.
Let's see, if we take this and we act on something else, right? Like we would have e to the add. Now what should this act on? Something in the Lie algebra, right? And so on this thing, that would be like the identity plus the add of x, Servon notation, add sub x, right? Plus 1/2 add x squared plus 1/3 factorial add x cubed. Right? And so that would actually mean what? It would be something like y plus the add x of y, right? Plus 1/2 add x of y, and so forth, right? Whatever that is. On the other hand, this, if we act on y, right? What would that mean?
Is that like add sub e to the x? Like, okay.
No, this is add, like, well, yeah, it is.
Or is it like eta? Well, yeah.
It is add sub, it has to be that, doesn't it? Or doesn't it?
Or is it like
What is
eta
this?
instead of
Otherwise,
Can it
what
be-
is this sub?
It can't be add of, yeah, it can't be add
No, it
sub
must-
e
it
to
must
the x,
be-
that doesn't make sense, e to the x is in the group. You know, like, it has to be like an eta,
Well, no, it's an a supposed to be in the group.
yes. I think it's just add, oh, you think it, I mean,
Well, I think it's like the eta function.
I should write this as add
E
e to the x to be more consistent with my other notation.
Right.
Because it's like add sub a.
Right. like the add function is like the A
Right.
that we defined.
Yeah, let's do that. The notation will drive you batty here. All right, so what that means then, of course, is I better check. A e to the x y, right? E to the x inverse. E to the x inverse is e to the minus x. We proved that other day, right? Huh. It's weird to me. How can I? Let's see here. Let's just go on. Well, maybe I want to leave these formulas up here. Maybe we can make more sense of them as we. It's not. Doesn't look to me like he's gone down this road. He just writes that, and he says where. I think he's making an identification though, right? Well. All right, finally, anyway. So proposition 2.24, let's talk about that one. And maybe that'll help us make more sense of what we're doing here. Okay, so proposition 2.24 says what? Proposition 2.24 says let G be a matrix Lie group, frac G it's Lie algebra. The adjoint, as usual, Lie group homomorphism defined above, and a little adjoint that we've been discussing. All right, here we go. G and G as before. Let's see here. The adjoint, I'll just write the stuff we're struggling with the most. G goes to GL frac G, this big adjoint. Lie group homomorphism defined above, and little add be the mapping from frac G. So now this notation, see now he's using this notation.
That's like the A to
That notation basically says that add A, I mean this, when he writes this, he's already saying that add sub A is equal to add of A. And those, by the way,
right.
are invertible transformations from frac G to frac G, right? Okay, little add is mapping from frac G to the general linear, general linear transformations on frac G. Not necessarily invertible. You know. That's the associated Lie algebra map. Then what's the deal? What's the punchline here? Then the little add x of y is equal to the bracket of xy. All right. It's funny. This proposition 2.25 is what we're picking at here.
Interesting.
Which I thought was just maybe the structure of the book right here is like, this is true, let me explain to you why.
Yeah.
I think that's what's going on here. It's not that this is it's not that this was already known, it's that he's trying to explain why it's known. Okay. So can we prove this? Why is the little adjoint xy equal to the bracket xy? How do we prove such a thing?
Use the property of big add. That it's preserves the commutator.
Maybe. How did we define the little add though? I think you might be right.
I think you're above one where you said it was the
Yeah, if we
in
use
the tangent space. So
yeah, maybe if we use that way of thinking, let's try that out. So you're like little add. Let's see if we can't do that. Little add of x, right?
Mhm.
Acting on y should be equal to what? It should be equal to that differential at the identity, right?
Mhm.
Of eta. Eta is what he calls big add,
Big add.
right?
Yeah.
Is that right? Yeah. Now that is supposed to do what?
What is it acting on?
Oh, that acts on x, right? And all of that
X on Y.
acts on y. So let me think about this. Add a acting on x is equal to a x a inverse, right?
Right. So what's the differential of that? Just
Right. So what if I look at a curve, and if I want to differentiate it, maybe a good way to think about it is to differentiate a curve. Trying to think about how to think that.
I think what he does is he uses the e to the tx.
Oh, right. He goes back to something we had from the other day, right? Which was that the little add was the derivative of the big add at tx and then set t equal to 0.
Mm-hmm.
So that's his way of differentiating. His way of calculating the differential basically is that he looks at ddt of e to the. I've already forgotten it.
E to the tx.
E to the tx.
Or well, big add of the e to the
Yeah.
tx.
Sorry. Big add of e to the tx. Set t equals to 0 after that. That is going to be, as he calls it, little add of x, right?
And is that the same thing as what you were doing there? Or is that...
I think so, because we were arguing that this is really the differential at the identity of big add, right?
Mm-hmm.
Of x, right? So, that makes sense. So this is a curve through the identity. This is what I was trying to get to.
So e to the tx is the curve that we could use.
Right, that's the one parameter group through the identity. And so if you feed that into the adjoint, that gives you a curve, right? Differentiate to find the tangent vector and put t equal to 0 after that. Yeah. Okay. Sorry. And then so what he does is what?
Oh, add is acting on y, so... Yeah, you have the derivative.
Right, well, yeah. So,
Just
So
like,
e to the tx, y, e to the negative tx.
so he's like add x acting on y, ddt of this stuff he just basically brings the, he says that the y's got nothing to do with the differentiation, basically, right? It's kind of sneaky. It's like, guys, bring y inside into this formula, why not, right? Just bring it into the differentiation process. There's some analytical sleights of hand going on there, but that's okay. To bring the y, I mean, okay. And then, well, that,
By definition of the add.
right, by definition of the add, that's e to the tx, not inverse, y, e to the minus tx. You put t equal to 0 after all that's done. Now you got to do product rule.
Yeah.
Product rule pulls down x, y, and then minus yx. You can see that. Before you plug in t, you've also got the exponential factors there. When you put t equal to 0, you get e to the 0, which is I, and they go away. So like this pulls down, you can put it before or after, it doesn't matter. Right? It's either x, when you differentiate you get x, e to the tx, y, e to the minus tx, and then you get minus e to the tx, y, x, e to the minus tx. But then set t equal to 0, the e to the minus tx and e to the plus tx go to 0. And go to the identity, and then you're left with the commutator. So there it is. Huh. I guess if we, I'm curious, what is it, do we get anything from differentiating? Do we get anything from differentiating this proposition? What if we differentiate that? Does that give us anything? So you take the differential of it, you know? Taking the differential of this should say something like, well, I guess it's an identity though, maybe I shouldn't do that, I don't know.
With respect to what?
Right. Well, that's a question, yeah.
To A? I mean,
I'm thinking is if I differentiate the big adjoint, I get the little adjoint, right?
right. Which is basically what you just did. Since the little adjoint is the commutator.
Okay, let me stop my idle speculation. So that anyway, we have proved that the little adjoint is just the commutator, right? Okay. And then what else? Which one we prove? Then he says that we have proved as a consequence of theorem 2.21 and proposition 2.24, that thing we just did, the following result, which is that e to the adjoint of x acting on y is equal to conjugation by the exponential, basically. So he says it follows. Yeah, stupid throat. This is his proposition 2.25, which states the following. It states that e to the little add x, and I'll put some parentheses in, makes me happier, acting on y is equal to the capital adjoint sub e sub x, again acting on y, which by the way is equal to e to the x, y, e to the minus x. Which is what we assumed that was true because he told us it was true earlier. Let's see, how does he get, why is that true now? Can you guys, why is proposition 2.25 true on the basis of the other things we've done today?
Still not got there.
He claims it's theorem 2.21.
2.21, I think, pretty much has everything we need to show.
Is that the one 2.21 is the one I glossed over, yeah?
Yeah. Well, it's got. That's part 3 of it. Yeah.
2.21 and proposition 2.24. How is 2.24 involved? I guess proposition 2.24
Makes it the.
well, proposition 2.24 means that this can be rewritten how? What does proposition 2.24 say about this infinite series right here? What does it change it to?
The commutator.
Right, commutators. But not just commutators, right? Commutators of commutators of commutators of commutators of commutators of commutators.
Huh.
So forth and so on.
And.
Yeah, that's out. That's
Yeah.
really.
So I'm still not seeing how that gets us to.
Oh, I know. I'm just. Oh, how do you get from? How do you go from what's in the purple to this thing?
Yeah, basically.
Yeah.
Let's just start telescoping, maybe?
Oh, I proved. Man, I don't know if I have that calculation here or not. I think I've proved this directly before. It's rather beautiful. Let's see if I can see it over there. Let me get in there for a second. See if I can find that. Once upon a time, I worked out this book called Griner's. I'm not sure I'm saying that right. What was it called? It was quantum mechanics. Not quantum mechanics, let's say. It's group theory and physics, and I have notes somewhere I wrote on that. And in there, I think I've derived this identity directly in terms of commutators and such.
Yeah, this is. It tells us it's exercise 19, and it definitely spells it out.
Oh, okay. I bet that's what I'm trying to find.
Yeah.
Which I will find eventually if it appears. If I got this. If it's in the book, good.
Page 61.
I'm saying I can show you guys the calculation explicitly if that's what I'm thinking of. Number 9, you said?
19.
19. Yeah.
That's the one.
Right. Yeah, so basically what that says is that you can show that this unending, like through direct computation, you can show that this unending series of nested commutators is in fact equal to, you know, e to the x, y, e to the minus x. And he does mention it was obtained indirectly in proposition 2.25, which challenges us to try to circumvent that direct calculation, right? Mm-hmm. Like if we could just think, how does it do that? I guess it's got to be the theorem 2.21 I'm ignoring. Yeah. Which said what?
Said a lot of things.
Said a lot of things. Yes, let's see, so theorem
I mean,
I would wager,
the homomorphism, there's inverses, commutators.
yeah, it's got to be in there. Okay, well, I'm gonna go on that. I do think you guys are right, it's in there. We really should prove that theorem in its entirety at some point. All right, moving along though. Next section's on the exponential mapping. I'll just tell you the high point here. Basically, his point is that the exponential mapping is, all right, so we have this result that there exists, right? There exists an x in, let's say, GL and C such that y in GL and C, right, has e to the x equals to y. I'm not sure I'm saying that very accurately yet. What I'm trying to say is any invertible complex matrix, all right, is reached as the image of some matrix exponential. All right. Now, if you're sloppy and you're thinking, you might be like, oh, then the matrix exponential is a surjection, right? It goes from the Lie algebra to the Lie group, it's a surjection. But the thing is, when we think about the matrix exponential for the Lie algebra, what we're doing is we're taking it and we're restricting it to a subspace of GLNC or GLNR. And there's it doesn't have to be onto. And he gives an example here of this matrix minus 1, 1, 0, minus 1. That is a special linear matrix of 2 by 2 over the complexes. And he explains why you can't exponentiate a traceless matrix to get it. And so, because we worked out before that the Lie algebra of SL2 is the set of trace. Because the determinant is 1, it forces the trace to be 0. When we look at the curve through the identity. And so that he gives an explicit proof then that SL2C, the exponential from little SL2, the set of traceless matrices, does not map onto big SL2, the Lie group. But then he gives this nice, somewhat technical condition about looking about a neighborhood, an epsilon neighborhood of 0, right? And he looks at the image under the exponential of that, and he says, it's basically, he gives a specific condition for a local inverse. He gives a criteria for invertibility of the matrix exponential on a neighborhood of the 0 matrix. And that's theorem 2.27. And, well, the proof of that is then given by lemma 2.28. And it goes on. And corollary 2.29, if G is a matrix Lie group with Lie algebra frac G, there exists a neighborhood of 0 in the Lie group, in Lie algebra, and a neighborhood of V of the identity in the group, such that the exponential mapping is a homeomorphism from the neighborhood of 0 to the neighborhood of the identity. So it's suitably restricted. The matrix exponential does in fact give us a continuous mapping with continuous inverse from basically mapping from 0 to the identity in the group. But it doesn't get the whole group, all right? We define the inverse to be the logarithm for G. I think that will turn out to be a restriction of the general logarithm we looked at the other day. I hope. Now he then proves that if you have a connected Lie group, every element can be written as a finite product of exponentials. So it's a very nice result, right? Like we just said, you can't cover the whole Lie group with the image of an exponential function, but what you can do, if it's a connected Lie group, you can take finitely many exponentials